We're going to get started now. Welcome, everyone. My name is Ryan Fioravanti. I'm here today from the Gmail team to talk about building fast mobile web apps. And if you'd like to follow along on your laptop or device, the URL is up here. You can see the slides at rjf-io2012.appspot.com. Okay, everyone loves fast stuff, especially users. And developers like building fast things. Unfortunately, on the mobile web, it's really difficult to do. Today I'm going to try and present a few things that I hope you can use to help build faster mobile web applications. When I start looking at performance work, I like to approach things in a very structured manner. What that means for me is before I start working on some improvements, I like to measure first to prove to myself that there's actually a problem that I'm trying to solve. As I start working on the problem, I then remeasure throughout the process to make sure that I'm making progress in a way that I'm happy with. And finally, when I think I'm done, I'll measure again to see that I actually had the impact that I thought I would. And if I didn't find an improvement, I think it's really important in those cases to investigate and figure out why the work that I did didn't have the impact that I thought it would. I've seen a lot of people spend a lot of time trying to make performance optimizations based off hunches they have or ideas, and they spend a lot of time. And when they're done, it ends up having no impact for the users, and there's no benefit. So we want to avoid these kind of situations. With this kind of thinking in mind, with this kind of approach, I decided to structure this presentation today around a live website. So I decided to pick on html5rocks.com, the mobile version. And what we're going to do is do a little bit of exploration, a little bit of measurements, try to identify what kind of problems it has, what kind of fixes we can make, and how much we can improve this. Okay, so before we start working on improvements, we first have to measure to figure out what's actually wrong. The best way to do that is by using a device to do all these measurements for us. Now that you all have Chrome on an Android device, this is really easy for you to do. And Chrome on the Android comes with a really neat feature where you can use the remote debugger to do profiling on the device itself. And this is really useful because profiling on your local desktop browser, for example, is not at all the same as profiling on your mobile device. The hardware is very different, the performance is really different, and so we really need to do all this profiling on a mobile device. We're also going to install the page speed extension, and this is going to help us run a bunch of automated analysis on the page, and hopefully we can get some quick wins based on its recommendations. Okay, before we get started with page speed or anything else, we need to define our success criteria. So to do that, we need an accurate way to make some measurements and figure out if we're actually improving anything. Typically, this has been done in a couple of ways in the past. One of the most common ways that developers would profile their application or do measurements for performance timings was to add timings in script blocks throughout the page. So it was really common to see people add a script block at the top of the document where they would take a time, and that would be time 0. And then they would have timings throughout the page, which they could then use the deltas of to decide how long certain parts of the page took for the browser to render. There's a couple of problems with this that we want to avoid. Number one, just by adding these measurements to your page, you can actually have a negative impact on the browser's performance. So just by measuring and looking at it, you're changing the situation. So we want to avoid that. But also, using this technique, we were only able to measure things that were happening in the browser after the browser has received the page content. We didn't have access to things like how long did a redirect take, how long did the DNS lookups take, how long did the page take to download from first byte to the last byte being sent to the page. Using this window performance timing object, we're able to capture all of that information really easily. This is an object that's injected by the browser on every page load, and it contains a lot of different attributes that we can use to analyze the full page load sequence. So this is really cool, and we're going to use this in a bunch of experiments that we're going to do throughout this presentation. The ones that I found particularly interesting for the experiments that I was running were these four. So first of all, the most important one is the navigation start timing. This is the exact time that the user requested for the page to be loaded. So this is them clicking a link to go to your page, or typing in the URL, or opening a bookmark. From the user's perspective, this is time 0, And everything after this time is them sitting there staring at a white screen, waiting for your content to appear. The response start event is the second one that was interesting to me. This one is when the browser has started receiving content. So this is important because this tells me when the browser is able to actually start doing work. It's not waiting for the page to load over the network. It can start processing the document, executing JavaScript, and evaluating CSS. The next one is this DOM content loaded event start. This is basically the DOM content ready event. And this one is important because this is when your document becomes interactive and can start handling events. And this is our best approximation for when the user actually sees something on the page. And this is important because this is the time for the start of this that I'm going to be optimizing for when the browser gets the page to when the user sees something. We want the user to see something as soon as possible, because until that point, they're just staring at a white screen. So DOM content ready means the user is no longer staring at a white screen. The load event is the window load event, and this is when the browser is finished downloading all the resources on the page, including the images. So this is like the final finish point. Okay, so we had to set up a baseline for the experiments before we start making any performance improvements, and this is what I came up with. So the way that I set up my experiments here is I created a local copy of html5rocks.com, the mobile version, and I set up an experiment where the browser would reload the page 50 times and capture the time from response start to the DOM content ready event. So what I wanted to optimize for was just the in-page rendering, none of the network stuff, just optimizing how fast we can show the user their content and stop staring at the white screen. And for this experiment, all the resources are cached, running on NexusS hardware, and using window.reload to execute the page reloads. So our baseline here is 1,200 milliseconds. So 1,200 milliseconds from the browser getting the first byte of the document to showing the user something. And so that's what we're trying to improve on now. And also 812 kilobytes transferred for the page. So the first thing I tried was page speed. So you can just open your Chrome debugger on the Android device and open up page speed, and you can run an analysis. So what it told me right away is, hey, you got some images that aren't scaled properly. So this is a pretty easy fix. We just have to scale the images. So I just modified the local version to serve up images of the right size. The images we were serving were actually way too big. They were 369 by 369 as opposed to 75 by 75. So a lot of wasted space there. And also these were avatar images, people's photographs, served up as PNGs. So I fixed that issue, reran all of my experiments, and these are the results that I saw. We had a 2% improvement in rendering time of the response start event to the DOM content ready, and we saved about 67 kilobytes. So this isn't actually the kind of improvement I was hoping for. I thought we were going to be able to do much better here because we're serving up much smaller images, and I just assumed that the browser would be able to render the page much more quickly, but that wasn't actually the case. But we did save some bytes, so that's good for users' bandwidth. So at least we have that. The next thing I realized is, hey, these are avatars. We shouldn't be serving them up as PNGs. We should be using JPEG. And with JPEG, we can get much better compression as well. So I changed the JPEGs, and I remeasured everything. Here we have another 2% improvement in rendering time. We're still talking only about tens of milliseconds saved. So this isn't really anything to get excited about yet. But we did save another large chunk of the payload size. We're only serving, we saved over 300 milliseconds here, which is a 44% improvement in the download size. So when the resources aren't cached, the page is going to load faster, and we're going to be using less bandwidth for the users. So again, no big improvement in rendering time, but still a really useful optimization for us to have made. Back to page speed, it's now happy with the scaled images, and it's telling us now you got to minify some JavaScript. So that's also a pretty easy fix. I opened up the network trace just to kind of see what resources it was loading, and I found that the page was including the full version of jQuery. So that's an easy fix. I just opened it up, saw that it's actually the full version. And then we can just swap that out with the minified version, save a bunch of bytes. The page functionality remains the same. This is a really easy fix to make because it won't actually change anything. And then we can remeasure. This is the one that surprised me the most, because here we significantly reduced the amount of JavaScript, but we didn't actually improve the rendering time at all. the rendering time remained constant from the last set of experiments. So that's not good. But again, we saved some bytes, so we should do this. It's the right thing to do. It'll be faster when the resources aren't cached, and that's good. So I said that we should always measure before and after, so that's what I did here. And if it doesn't match the results that you expected, we should figure out why. So this is one that really surprised me, and I figured out the answer, and I'm going to show you that a bit later. So when you need to minify, this is something you should definitely do to save bytes over the wire. If you're using a third-party library, just make sure you're pulling in the right version for your production environment. So you usually want to include the dev version in your local setup, but when you deploy to production, you should have some kind of build phase where you swap it out with the minified version, and that's easy to do. If you're writing a lot of your own JavaScript, then you're going to have to do your own minification. This is something that you can also set up into your build phase. There's a couple of tools you can download as command line tools that you can run in your files, and you run this tool and it spits out the minified version for you. Or if you just want to quickly minify some stuff, you don't want to download anything and get this set up, there's an online version as well that you can try. You just drop some JavaScript into a text area, click a button, and then you'll get the minified version. OK, so the next thing that I wanted to try, we're done with page speed now. We've satisfied all of its recommendations. The next thing that I wanted to try is to run some CSS profiling. So using this, I can take a look at exactly how expensive my CSS rendering is for the browser to execute. So to do this, open up your developer tools on the Android device, go over to the Profiles tab, select the CSS selector profile and click Start. And this will start a recording of how expensive your CSS is. So what I did here is I did that, I clicked Start, started recording, and then reload the page, and then I stopped the recording. And this tells me how expensive the CSS is during the page load. And here's the results. So here we get a breakdown of exactly how expensive every single CSS rule is in my style sheets during a page load. And so it's telling me here, this rule at the top, I've sorted by the total time taken for each rule. The rule at the top is taking over 50 milliseconds for the browser to evaluate while the page is loading. This is rendering time that the browser is spending before showing the user any content. So it's telling me just by fixing this rule, I can save the user 50 milliseconds in wait time. So that's pretty cool. And there's also a bunch more rules here that are over 20 and 30 milliseconds. So if I fixed all of those, I'd be looking at hundreds of milliseconds in savings. So that's something I'm interested in. So I dug a little further. Before I show exactly what was wrong, I'll talk a little bit about what can make CSS expensive on mobile. Mainly, it all boils down to how many elements is your CSS selector matching. So if you're matching all elements in your document, that's going to be really expensive for the browser to work with. This is why the universal selector is so bad on mobile, because it has to, the browser has to apply that to every element in your document. Also, ancestor rules are pretty expensive, because when it finds a match for the rightmost element in the selector, it has to search the ancestor tree of that element, further qualifying to find a match for that rule. So what I've got here, this body star rule, this is about the worst CSS rule you could possibly write. This is the universal selector matching everything in the document, which we already know we shouldn't do on mobile, but also with an ancestor selector of the body. So the browser has to enumerate every single element in the document and then search the ancestor tree of that element to ensure that it has an ancestor of type body. So this is really expensive, but it's also wasteful because, of course, every element is in the body. We really don't need to qualify this. Here's some examples of ways you can change your CSS from bad to good for these different cases. So first of all, we know we want to avoid the universal selector. The way to avoid this is to just kind of realize that most of the time you don't actually need it. Say, for example, you want to apply a consistent font to your entire document. You don't need to use the universal selector to do that because CSS has this cascading nature. You just apply the font rule to your body, and then your entire document will naturally inherit that rule. So that's an easy fix. For consider rules, these are pretty standard rules, the UL, LI. If you want to color all of your list items blue, that's a pretty standard way to do it when we learn CSS. But if you swap that out with a specific class name called unordered list item that you manually apply to all of your LI elements in the document that are children of UL elements, This will execute much faster on mobile hardware, and you will see a difference. Lastly, don't include CSS rules that set things to their default values. Like here, I've got div set to display block. Just let the browser figure that out. If you're trying to save like some rare user agents that might have screwed this up, then I would say just let most of your browsers be fast and let broken browsers be broken browsers. Okay, so back to the example, HTML5rocks.com, we had that 50 millisecond timing on one rule. And turns out that it was specifying a default CSS property, setting the box sizing of every element in the document. So this one is really easy. Because it's a default property, we can just remove it. The page will have the same behavior, and we can figure out what kind of impact it had. So here we go. Approximately 50 milliseconds saved in rendering time. That's just about exactly what we expected. That was nice to see. I was comforted by this because the profiler told me when I measured before that I would save 50 milliseconds if I fixed this rule. And then when I measured after, that was confirmed. So what this means is that the profiler is doing an accurate job of predicting exactly how much my users will save in time if I fix those rules. So that's good to know. So if you are planning on setting out for a couple of days or a week to optimize the CSS on your page, you can be sure that you should definitely open up your CSS profiler and check, are there actually any problems? And if not, then you can just skip that whole process. Okay, so what's next? Remember what we're trying to do here. We want to optimize the time for which the user is sitting there waiting, looking at a white screen. From the time the browser gets the page to the time they want to see content, we want to get rid of everything on that critical path. So if we look at the network trace in your developer tools, you can see exactly when that DOM ready event is firing. That's the blue line. So this is our approximation for when the user is seeing content. Everything on the left of this is just getting in the way. So we need to make sure that everything over here is something that's critical to showing our user content. So here's the first resource. Obviously, this is critical. This is the main markup of the page. Our CSS is pretty critical. We don't want to show people just plain HTML. But then the rest of these are all JavaScript files that are loading over the network and taking time to execute. So on HTML5rocks.com, this is just a plain website. We don't need to include all these scripts before we show the user something. And the problem with these is just the presence of these scripts on the page that's slowing down the DOM content ready event. When you include a script on your page, the browser doesn't actually know when it should do something with it. It doesn't know if you need that script immediately or if you just need it like 10 seconds from now. So what it does is it downloads it immediately before doing anything else, before it proceeds with the rest of your document, and then it executes it right away too. So if, in this case, we don't need that kind of behavior, we can defer this JavaScript until later. So we have to do we can do something here in order to get rid of that. So what we need is a way to defer this JavaScript in a reliable manner. I looked at a couple of ways to do this. First, I tried the defer attribute. This didn't work well for me. I tried it, and it worked. But when I reran my experiments, it didn't actually help anything. When I investigated a little deeper to find out what was happening, I found a lot of resources suggesting that the defer attribute is more like a suggestion to the browser. So it can defer it if it thinks that's a good idea, or it'll execute in parallel if it has idle cycles. I also found a bunch of stuff that it's not good cross-browser and all this stuff. But point is, it just didn't really work well. It didn't speed up the page rendering time. I then looked at the async attribute, and this had some different behavior where it would defer the loading of the scripts, but they would load in at any order, not necessarily the order that you include them on the page. So this can lead to some race conditions where you get JavaScript errors if you say you have some inline script running jQuery functions before the jQuery file gets loaded, then that's not going to work properly. So what I did is I cooked up a way you can include a special type on your script attribute that tricks the browser into thinking that this isn't actually JavaScript. So what we have here is I've just stamped all these script elements with a special type called not.js. And so now these scripts will actually download over the network. But the browser will just pass over these and not do anything with it because it doesn't know what it is. And then when you want to load these scripts, you can just include this simple bit of script here. What this does is it loads all the scripts in the document, loops through them. If the type is not JS, then it sets the type back to text JavaScript, and then it re-adds it to the document. When you do this, the document reevaluates it, parses it right away, because now it sees that it's JavaScript, and executes it just as we would expect. So what I've done is I modified the experiments, created this function, added not.js to all the scripts on the page, and then I set this function to be the window onload function. Here's the results. Ooh. So our page rendering time just got a lot faster. We have a 33% improvement in rendering time, and this is hundreds of milliseconds. But remember, all these resources are cached. That's how we're running these experiments. So why does this take so long? It takes so long because it takes 1 millisecond to parse every kilobyte of JavaScript on modern mobile hardware. And this is really important. What I mean by parse is when the browser encounters a script block, this is the time that it takes to read all of the text in that script block and figure out what it means in terms of JavaScript, and then execute all the top-level lines of JavaScript in that script function. And this is much more expensive to do on mobile than it is on desktop. Here's a more detailed breakdown of some of the experiments that my teams run to investigate what kind of parse times we see across devices. So you can see here for Nexus S hardware, it takes 300 milliseconds to parse 300 kilobytes of JavaScript. And that's where we get our 1 millisecond to 1 kilobyte rule. And 300K is a pretty average amount of JavaScript to include on a page, especially for pages that have kind of been ported over from desktop, where we just include lots of JavaScript all the time and it doesn't really matter. And 300 milliseconds is a long time for your user to wait, staring at a white screen, seeing nothing, waiting for your page to load. Now what's really interesting is looking back a few generations in phone hardware, and we see that an iPhone 2G would take over 3 seconds to to parse the same amount of JavaScript. And that's a 10x improvement in just a few generations of phone hardware. So what we're seeing is a trend where phone hardware is improving drastically very quickly. And so you should keep this in mind. It should play a pretty big role in how you think about performance optimizations. Now let's think back our jQuery example. We minified jQuery and we saved over 100 kilobytes in JavaScript, but we saw no improvement in rendering time. So why was that? So in this table, you'll see, or maybe you won't see, these are for minified JavaScript sizes. So when we minified our jQuery file from 240 kilobytes to 90 kilobytes, we didn't actually make it any less complex for the browser to parse. It's still the same JavaScript. It still has the same level of complexity, the same amount of stuff to execute, and the same amount of stuff for the browser to figure out. So just by minifying it, we didn't actually save anything in parse time. So that makes sense. What this also means is that you shouldn't just minify your JavaScript. You should compile it. Using tools like Closure Compiler, you can run phases like the dead code removal in order to get rid of all the JavaScript on your page that's not actually being used. So when you're pulling in libraries like jQuery and using only a small fraction of it, you can use compilers to remove all the stuff that you're not actually using. And when you do that, that's when you're going to see improvements in parse time. OK, so how much faster can we go now? We have optimized images, optimized CSS, and no JavaScript getting in the way of our content rendering. The only thing we could do now is get rid of styles, which we probably don't want to do, or send down a smaller DOM. So we could just say to our designers, hey, your document's too big. I don't want to show this much content. It's really expensive on mobile. And maybe that's acceptable. But say it's not. There's still something that you can do. Here's a little trick. We're going to lazy load a bunch of the document. So we can send down large portions of the document and only show a little bit on when we're first rendering the page. When the HTML5rocks.com main page, it's got a lot of scrollable content. So there's a lot of stuff when the user loads the page that's there, but they can't actually see. So there's no reason for us to actually demand that the browser try and render that right away. So what I've done here is I took a couple of the top-level elements on the web page and set them to display none, which just takes it out of the rendering process completely. Then on the page load, we can just set these back to display visible, and they'll show up right away. So they'll be there by the time the user scrolls down to try and use those parts of the page. And by doing this, we've made the page significantly simpler for the browser to render. And now we've saved another couple hundred milliseconds in rendering time. So now we're sitting at 600 milliseconds of render time. So remember, that's time from the browser getting the page to showing the user content. And that's just about a 2x improvement since we started these optimizations. So at this point, I'm pretty happy. And I don't know that there's much more we can do on just the rendering other than waiting for newer phone hardware. We could maybe squeeze out another 50 or 100 milliseconds in this rendering time by really digging into the CSS or simplifying the DOM a little bit more and stuff like that. But at this point, our effort is probably better spent optimizing other things. So far, we've only been looking at the rendering performance, but there's actually a lot more variables that the user waits on other than just the rendering. We need to consider things like the network load time and redirects and all this kind of stuff. And optimizing for these is really hard to do on your local development environments because the environment is completely different from the production environment. So to figure out what real users in the wild are experiencing, there's this cool website called webpagetest.org where you can go and they've got a browser farm and you can type in any website URL. It will load the page and tell you exactly what kind of load sequence your page has. So these are the results for HTML5rocks.com using one of their Android browsers in the mobile browser farm. So here we can see exactly what's happening on page load. We've got 2 redirects here, and then here's the main page load, and then all these resources loading in. Here's the rest of the waterfall chart. So right away, we can see exactly how much time we could save the users by optimizing different parts of this process. For example, why do we need 2 redirects? We could just get rid of one of these redirects, and we would automatically save 100 milliseconds right there. But it looks like the biggest performance improvements we could make here are on this page load. It's taking over 1.7 seconds to download this page. That's pretty terrible. Also, interestingly, is that these browsers and the browser farm are all on a strong Wi-Fi connection. So it's not like this is downloading over an edge network and taking a long time. This is probably taking over a second just in server processing time. So if we really want to make a difference for our users, we would look at this information and dig into our server infrastructure and figure out why it's taking over a second to process requests and start sending the first byte to the browser. And here's the green line. This is the load event, and you can see there's a bunch of JavaScript files loading. This is what we've pushed over onto the other side of the ready event. And remember that we saved 600 milliseconds, which is maybe about like this much. And we said that the only further improvements we can make there are pretty marginal. So definitely looking at this huge chunk here, this is what we would want to focus on if we want to help our users out. OK, so what if we decide improving the server is hard? I want to do this from the client. We actually can do that by using app cache. And using app cache, we can entirely get rid of the network time and bring that to 0, because all the resources will be cached locally, including the HTML file. To set this up, you just need to create a manifest file and link it to your HTML attribute here. You host this manifest file on your web server, and in this manifest file, you describe all of the resources that you want to be cached. So when we add that to the page and rerun the experiments, we see that we've actually taken a rendering hit. And so this was important and a little bit of a surprise to me. Upon investigation, I realized that what was happening was the manifest file is downloading on every page load. Even if all the resources are cached, the browser has to re-download this manifest file every time it opens the page. And that's because the manifest file it serves as the indication to the browser as to when it needs to update the resources because the application's out of date. So when the developer changes the manifest file, that means the app needs to be updated, re-download all the resources. But what it means for a normal page load sequence is that we've downloaded the page, and the first thing the browser processes is the HTML node. And it sees the manifest attribute, and then right then and there, it starts downloading this app cache file. So that means while you're on the critical path of trying to render your content, you've initiated a new download happening in parallel. So you're creating resource contention, and that's why we see the rendering hit. However, this is pretty acceptable given that we're saving, as we saw, almost 2 seconds in network load time. So that pretty far offsets the tens of milliseconds that we're losing here. Okay, so app cache sounds pretty easy. I'm making it sound like a silver bullet to improving your network time, but that's not actually the case. It can be a real challenge, it can be a real nuisance, and there's lots of things that can go wrong. Let's talk about why, and it requires a little bit deeper understanding of how app cache works. So what we're doing here is looking at the resource tab. This is showing us the app cache entry for the site on the local version that I've created. These are all the files that have been added to this app cache entry. The manifest file is the key to the app cache entry that maps to all the resources that are cached in this entry. So all the resources that you list in the manifest file, you can find them all here. These are the explicit entries here. All of the HTML files that point to this manifest file end up in here as master entries. So if you have 10 pages on your site, all pointing to the same manifest file, they'll all appear here as master entries in your app cache entry. And then remember, when the manifest file changes, that's the signal to the browser to re-download the resources because the developer has published an update to this application. So when that happens, you can see how the browser behaves by looking at the developer console when you're refreshing the page. So what happens is the browser sees the manifest file has changed, and then initiates an app cache update and re-downloads all these resources. And what we see here is it's downloading these two HTML files at the same time. Let's look at an example of why this can be so bad. Number one, user opens a single page with 5 external resources. Let's say that totals 350 kilobytes of downloaded stuff. That goes into the app cache entry. The user then opens 10 more pages on the site. Each of them are 200 kilobytes. All of these go into the app cache entry. Now we publish an update to the web app by changing the manifest file. The user visits just one of these 11 pages. The browser checks the manifest file, sees a change, and initiates an app cache update. And now what happens is the browser downloads over 2 megabytes of data in the background just by navigating to this one page. Say you had 10,000 users that day. You're serving up over 20 gigabytes of data versus what should have been only 20 megabytes of data if they were just loading those HTML files by themselves. So not only can this be really expensive for your users, but it can be really expensive to you depending on your server infrastructure. Okay, so how can we get around this? The obvious solution seems to be, let's include one manifest file per HTML page. So for every page we're serving up, it's going to have its own manifest file. It'll have its own app cache entry, and everything will be good. That's not actually the case either. When you create several app cache entries, you can use Chrome, go into app cache internals, and see how you're kind of affecting the various app cache entries in the system. So what I've done is I've modified the local version to have several app cache files for those 2 HTML files that we were previously loading in the single entry. What we see here is this one here is over 350 kilobytes in size, and this one is also very large, over 260. And what's happening is that all of the external resources that our manifest files are pointing to are being cached in both of these app cache entries. So the app cache entries can't share external resources amongst themselves. They need to cache all of the files explicitly in each entry. And so the sizes of these are adding up quickly. And the reason that's a problem is because the browser has a hard limit of 5 megabytes per domain quota for your app cache space. So just based on the pace that we're going here for HTML5rocks.com, by only adding 10 pages to this app cache setup, we would exceed that limit already. And what happens when you exceed the limit is the browser tries to download the updates, and when it gets the update, it tries to push it into the cache. But when you're exceeded your quota, that push will just fail. And there's nothing that you can really do about it programmatically in JavaScript. If your users get into this situation, they can actually get stuck on a really stale version of their site because they can't actually update to the new version. So this is a pretty big problem that you should try to avoid. And if you get into this problem, you're kind of screwed because you can't fix it after the fact. The only thing that you can do is serve 404s on your app cache requests, and this invalidates the app cache in the browser. Okay, so it used to seem really easy, now it seems really hard. How can we actually make this work? You have three options, basically. You can decide to only include a manifest file on a select few pages. So this means maybe your home page or just a few really important pages include a manifest file and use app cache. So this is acceptable maybe, depending on your product requirements. But what this does is basically limit the scope on how big your app cache entry can get. The next thing that you can try is to implement your entire site as a single page. So this is more kind of what those like web app apps do, where it's just a single HTML, JavaScript, CSS bundle sent to the client. Gmail and Twitter are both good examples of single page sites that use app cache. And when you're doing this, you don't run into the problem of many pages because you only have one page. And the other option is to just not use app cache at all. Google Search uses a really cool technique where they want to cache lots of resources, but they want those to be cached across all their URLs, because when you do a search, it modifies the URL so that's shareable and things. So they're saving a lot of stuff in local storage and caching their resources that way, such that they're available across all pages. Okay, so let's change gears a bit. So far, we've only talked really about page load and rendering time. The next really important thing on mobile is event handling time. Basically, everything that happens after your page is loaded is an event handler of some sort. And so what I really want to focus on here is the user does some kind of interaction on the page, and then we execute some JavaScript and publish an update to the application somehow. We change the DOM so the user sees something happens. And so there's a couple of high-level guidelines here. First of all, everything on the DOM is slow. So touch it as little as possible. And when you do touch it, we want to batch all of the DOM changes together. If you're at the jank busting talk that just happened an hour ago, they showed a couple of really cool ways that you could debug these kind of issues. And this is a little bit of the same thing, but kind of different. So here's an example of a really bad event handler. And this is how you can debug it and see what's going on. So using the events timeline, we see here is the event handler, and I've expanded this, and now we can see what's happening in this event handler. And what we see here, these are recalculate style events. What we see here is we execute some JavaScript, and then we have a style recalculation. Then we execute some more, we have a style recalculation. And every time there's a style recalculation, this is what's really expensive, especially on mobile. This is where the browser says, hey, wait, I got to update stuff. And it basically does a reflow of the entire document to calculate how large all the blocks on the page are. And that's why we see this big time gap here. This time here is the browser just taking time to lay itself out again. And then we have another reflow here and another one. And then here's the paint event here. And this is the real goal of the event handler, is to respond to the user's event and paint as soon as possible. Here's the code that is the implementation of this really bad event handler. And so what we have here is a bunch of DOM mutations sprinkled throughout the event handler. And this is exactly what we want to avoid. And then what we have is we're just using this, we're looking at offset width of one of these divs. And using offset width is something that requires the browser to know how large things are on the page. So it needs to do a style recalculation. So each one of these offset width statements here is what causes the style recalculation and is what's making this event handler so slow. Here's a re-implementation, just simply rearranging this function so that it performs significantly better. All of the DOM mutations are batched together, and then based on these statements here, we'll only end up with one style recalculation. So here's what it looks like now. The event handler fires, we execute a bunch of JavaScript, we have one style recalculation, and then we do our paint. And so this is significantly faster and will end up being much more responsive feedback to our user because the paint happens so much closer as to when they interacted with the page. Here's the kind of performance impact this can actually have. So I ran just this simple bad code snippet on desktop Chrome 1,000 times, and it took 9 seconds for the bad case and 2.5 seconds for the good implementation. This is a 72% improvement in the processing time of this event handler, so that's really significant. And then on mobile, I ran it 100 times on Chrome for Android, And similarly, saw a 66% improvement in the handling time. So this is really important to do for any time that your user on your touch-based mobile web application, when they touch something, they want to see an update as soon as possible because they, A, want things to be fast, but B, when they touch it, they need that kind of tactile feedback in order to feel like the application is really performing properly. Okay, so the next thing that can really hurt your interaction speed is the 300 millisecond problem. This is the problem where all click events on mobile browsers come 300 milliseconds after the user actually taps the screen. And the reason that browsers do this is because they're waiting to see if the user taps the screen again, which would indicate a double tap. And so a double tap on mobile browsers will perform a zoom-in operation. And so that's why they introduced this delay. For us, if we're creating an app and we have a button, we don't really want to have to support the user zooming in on a button. We just want that button to respond as fast as possible. And by the time 300 milliseconds executes, we're way too late already. There's nothing we can do, no matter how efficient our event handler is, it's going to be too slow. So the way we fix this is actually really hacky. I've got a code snippet here that kind of illustrates how we can do this. This overrides the default functionality of the click event, sets up touch end event listeners on the button, and then on the touch end, we'll do whatever click behavior we wanted the button to do in the first place. And then you can get a handle on your buttons throughout the application in JavaScript and decorate them with this behavior. And all of a sudden, your buttons will be magically fast. So I make this code snippet seem really simple, but there's actually a lot of problems and glitches that it introduces and considerations. So for more details, check out this article that I wrote a while ago on creating fast buttons for mobile web applications. It explains all of the things that you need to keep in mind while you're working with this approach. And if you don't want to have to write code yourself, because developers are lazy, which is good, you can pull up this implementation here on HTML5 boilerplate /mobile, and you can just drop this into your app and start using it. Okay, so the next thing that we want to be able to do when we're providing the user with DOM updates is to make sure that if we're doing animations and things like that, that they're as smooth as possible, which will make the user happy, hopefully. And so the way that we need to do that is make sure that all of our animations and document updates are hardware accelerated when necessary. So hardware accelerated means that you're going to take an element, it's going to be turned into a layer that will be uploaded to the GPU for processing off the main thread. And this is what allows it to be really smooth and really fast. Making something hardware accelerated in your document is kind of magical today. You just have to do something to put it in some 3D space, and that will hopefully make it hardware accelerated. So you can create a class like this in your CSS rules called hardware accelerated. WebKit transform is the identity transform. And you can apply this to elements. It won't move it anywhere on the page, but now updates to this element will be hardware accelerated. Now, if you're moving elements, you can create a different class. You can move elements using the positioning attributes like left or top, but it's actually much faster to use the transform property to move elements. So this will ensure the best hardware acceleration possible. So what we have here is a little CSS rule to make something transitionable. We will apply a transition, which will be on the transform property. This transition will take 200 milliseconds to execute, and we'll use an easing function. Okay, so we're going to put these three ideas together now. The three ideas were efficient event handling, solving the 300 millisecond problem, and smooth updating of elements using hardware acceleration. So consider a scenario. In your mobile web app, you've got a button, and when the user taps that button, you want to do a view slide transition to the next page. And you want this to happen as fast as possible. The next page isn't rendered yet, so we need to render it when the user taps this. And the next page needs to become interactive as well. So not only do we need to render it, but we need to add a bunch of event listeners to it and maybe load in some images and stuff like that. So here's a nice approach we can take. First of all, we'll set up a couple of CSS rules for our 2 pages that will make them transitionable. Next, we'll take our button and make it a fast button to avoid the 300 millisecond problem. Now when the when the tap event occurs, we'll get a handle on the current page and the next page. We'll render the next page, but we're going to be very careful to only do a minimal amount of rendering possible. So we don't want to render everything because that will take too long. We want to start this animation as soon as possible. We then apply our transform properties because using transforms is a better way to reposition an element. And we're going to do it such that the current page animates off the screen and the next page animates onto the screen. Remember, we want to make the next page interactive. As soon as we apply these transforms, the animation will start. But we still have to do additional work on the next page to load in those extra resources, images maybe, and add event listeners to it. So we can add an event listener which will fire as soon as the transition ends. And when it does, now this is the appropriate time to do all of that additional rendering and an event setup. So what we have here is probably the ideal event handler. It's a fast button. We do a minimal amount of DOM changes, and all of our DOM changes are batched together. And then we defer all of the expensive work until after the animation starts. And our animation is hardware accelerated. OK, so that's all I have for you today. Here's a kind of summary of the various optimizations that we did. And some of them were a little bit surprising. So again, that's why it's really good that we measure things. So we don't just assume what's going to happen. We confirm that it behaves as expected. And these are some of the tools that we looked at: Chrome DevTools, PageSpeed, and webpagetest.org. And if you're going to remember anything, please remember, don't waste your time. Always measure before and after. Verify all of your assumptions. And optimize what will make a difference, not just what's interesting to work on. OK, thank you very much. I'll happily take some questions if people want.
Hey there.
I can also stick around for a bit after if people would like to talk in person. But if you want to ask a question in front of everyone, just step up to the mic.
I was wondering if if jQuery Mobile uses most of the optimizations that you were just showing.
jQuery Mobile, I know, I'm pretty sure they have the tap functionality, like making buttons fast. I've also seen they've worked a lot on view transitions and things. When you're using these frameworks, they can try and do a lot of stuff for you, but based on all of your integration points, it's really easy to introduce slow points. So it's really important, even if you're using all these libraries, that you really dig in and understand what can make your app slow, and look at if it's being slow. Maybe jQuery Mobile does do all of this stuff, but you have to confirm that you're using it properly, because there's so much you can do to screw it up. So, yeah. Yep.
Yeah, I had a question about your really interesting technique for making the JavaScript load later by making it a different type. I've seen a lot of people do the technique where they put the JavaScript at the bottom of the page instead of in the head. How does that play into the decision?
Yeah, so I tried moving the JavaScript to the bottom of the page. When it's at the bottom of the page, the browser has just finished receiving the entire document. And so it's not clear whether it's being painted or not. And it then encounters the JavaScript, which may or may not be mutating the DOM, so it then executes all of that. So when I did that, it didn't actually have an impact on my experiments at all. And it kind of makes sense. Like if your script at the bottom is going to change everything in the document, then the browser should wait for that so that you can show the user the proper content. Does that answer your question?
What tool did you use to get the repeated page loads?
So at first, I'll be honest, I was actually just refreshing the page and looking at some of the timing output in the dev console. But then I got much smarter, and I created a loop kind of where the page would load, and then it would take my timing. I would save that in local storage, and then I would call window.location.reload. And also in local storage, I would save the number of times that I ran this. So when that counter got to 50, because I was running 50 samples, then I would stop calling reload, and I would just stop, and I would alert the average of all the times that I was tracking. So no tool, I just wrote something that used local storage pretty quickly. OK, thanks, everybody.